We also want to talk about the trig ratios of the angles in these special right triangles. So in part A, they're asking us to find the unknown side lengths and the trig ratios for the angles. All right, so it's a 45, 45, 90, and the legs are 1. So I know that my hypotenuse is radical 2 times 1, so it's just radical 2. And then I use the definitions of sine, cosine, and tangent to find those ratios. So they had this as 1 over radical 2, radical 2. And then they simplified it the way I did back here to get radical 2 over 2. So now we're going to find the trig ratios for the 30, 60, 90 triangle. The hypotenuse, remember, is twice as long as the short leg. So the length of the hypotenuse is 2. The longer leg is radical 3 times as long as the short leg. So the length of the longer leg is radical 3. So then this is radical 3, and this is 2. So I'm going to find the sine, cosine, and tangent of the 30-degree angle and the 60-degree angle. Remember that sine is opposite over hypotenuse, so that's 1 over 2. Cosine is adjacent over hypotenuse, so that's radical 3 over 2. Tangent is opposite over adjacent, so that's 1 over radical 3. But we're not going to leave it like that. Whoops, sorry about that. We're not going to leave it like that. You have to rationalize it. The sine of 60 degrees, that's opposite over hypotenuse, so that's radical 3 over 2. Cosine is 1 over 2, and tangent, that's opposite over adjacent, so that's radical 3 over 1. Any patterns or relationships we see in the tables in parts A and B, why do these patterns or relationships make sense? Well, we've already seen before the sine of an angle equals the cosine of its complement. And remember also that tangents of complementary angles are reciprocals. For what acute angle measure theta is tangent of theta less than 1, equal to 1, or greater than 1? All right. Well, we know that the tangent of theta will equal 1 when theta is 45 degrees. We saw that here. Notice that this tangent is less than 1, whereas this tangent is greater than 1. So, tangent of theta is less than 1 when theta is less than 45 degrees, and tangent of theta is greater than 1 when theta is greater than 45 degrees. We're asked here for the unknown side lengths and trig ratios for the 45-degree angles. Well, first let's find the side length. Like I said, there's a 45, 45, 90. So I know that the hypotenuse equals leg times radical 2. So 10 equals AC times radical 2. Now I'm going to do in this example the same thing that I saw earlier that I really liked. I'm going to multiply this whole equation times radical 2. When I do that, I get 10 radical 2 equals 2 times AC. And when I divide both sides by 2, AC, which is going to be the same as AB, is 5 radical 2. So the sine of 45 degrees, and it doesn't matter which 45-degree angle I'm looking at, whether it's B or C, equals a leg, which is 5 radical 2, over the hypotenuse, which is 10. Now this reduces to radical 2 over 2. Very interesting. Same idea with the cosine. It'll be 5 radical 2 over 10, which will reduce to radical 2 over 2. And then tangent of 45 will be 5 radical 2 over 5 radical 2, which is 1. Finally, in this lesson, we're looking at Pythagorean triples. So a Pythagorean triple is a set of positive integers. So think about what that means. Positive, you know what that means. Integers means nice, pretty numbers. So you can't use decimals, you can't use radicals, have to be nice, pretty numbers. Like 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, and 17. All of these numbers I can plug into a squared plus b squared equals c squared and get a true equation. So let's verify that they are Pythagorean triples. So that means that I'm showing that 3 squared plus 4 squared does in fact equal 5 squared, because that's 9 plus 16, which does equal 25. 5 squared plus 12 squared and 13 squared. 5 squared is 25. 12 squared is 144. 13 squared happens to be 169. 7 squared plus 24 squared and 25 squared. This is 49. This is 576. And when I add that together, I do get 625. And then the last one they wanted us to verify is 8, 15, and 17. 8 squared is 64. 15 squared is 225. When I add that together, I get 289, which happens to be 17 squared. Now, these are not the only Pythagorean triples, but I do know that multiples of Pythagorean triples will also be Pythagorean triples. Okay, so let's consider. DEF is similar to triangle JKL by the side-side-side similarity, because the corresponding sides are proportional. I can complete the ratios to verify that. A is to KA. Oh, nope, that's not the way they wanted it. A to B to C, rather, is equivalent to KA to KB to KC. Okay, in part C, we're going to use Pythagorean's theorem, but I have a typo alert. This parenthesis should be here, not there. Here, not there. So when I take Ka, the quantity, and square it, I get K squared A squared. And when I take the quantity Kb and square it, I get K squared B squared. So K squared is a greatest common factor in this expression, so I'm going to factor it out and get A squared plus B squared. Oh, well, I already know that in this triangle, a squared plus b squared equals c squared, so I'm replacing that here, and then I'm kind of going backwards. K squared times c squared equals kc, the quantity, squared. So that means that the set of numbers ka, kb, and kc form a Pythagorean triple. Suppose we're given a right triangle with two side lengths. What would have to be true for us to use a Pythagorean triple to find the remaining side lengths? So I'd have to know that the lengths are two of the numbers in a Pythagorean triple. Also, that if they're legs, they're the two smaller numbers. If a leg and hypotenuse they are one of the smaller numbers and the largest. Or multiples. And I'll clarify what I mean by that. For example, in this your turn example, I have these two legs. So it's asking me to use Pythagorean triples to find the unknown side length. So what do 18 and 24 have in common? They're both divisible by 6. Okay, so this is 6 times 3. This is 6 times 4. I know that 3, 4, 5 is a Pythagorean triple. So that means this must be 6 times 5, which is 30. Here I have a hypotenuse that's 68 and a leg that's 32. Well, what do 32 and 68 have in common? Well, they're both divisible by 2, but even more than that, they're both divisible by 4. Okay, so xz equals 4 times 8. xy equals 4 times 17. Oh, 8 as a leg and 17 as a hypotenuse. That's 8, 15, and 17. So that means that yz must equal 4 times 15, which is 60.